Thank you. So I was given the task of introducing a lot of the concepts that are going to come up in some of the later workshops. There are a lot of workshops, and there are a lot of concepts. So some of these include, for example, mathematical physics, and you would be forgiven for wondering how that relates to some of the topics we've seen this morning. There is, of course, a very strong connection. I don't think it was possible for me to explain that in 3 lectures. But that connection, in any case, comes via the theory of periods. So let me say something about that, first of all. So I guess this is an overview, first of all, of what I want to say. So I always recommend to students to read a paper by Kontsevich and Zagier, which goes by the title of Periods, which is immensely inspiring and is packed full of fascinating examples and shows how periods connect to lots of different parts of mathematics. I strongly recommend having a look at that. I can't do more than scratch the surface in terms of examples in this lecture, at least. The way they introduce the subject is very nice, very elementary, and they say that a period, I'm going to change the definition in a minute, but a period is a complex number whose real and imaginary parts are given by convergent, let's not worry about convergence, integrals of the form of a rational function in variables x1 up to xn, where p, q, and fi are a finite set of polynomials with rational coefficients. So when it converges, it defines a number, a complex number, and they call that a period. It's a very, very broad class of objects. So you can generalize this a little bit immediately. There isn't sort of standard terminology. I think it makes sense to call this a family of periods. People use different phrases. And I'll give the proper definition later on, but intuitively, a family of periods is the same thing where you have extra variables floating around. So you could, it's going to be a function now, not just a number. So it'd be the same thing where, what did I say? Where it's the same, where this time p, q, and f I depend polynomially on some extra variables. And typically this will be a multi-valued function. Because that's not a very good definition, but it gives you an idea of what I mean in the first instance. Okay, so examples. Some very basic examples. Again, that I strongly recommend looking at Kontsevich and Zagier's paper for more interesting examples. Very elementary example is square root of 2. Which is an algebraic number, and more generally you can show that in fact all algebraic numbers are periods. Here's another very basic example. The values of the Riemann zeta function, which are a priori defined as a sum so for n greater than or equal to 2. This number is also a period, and it's given by this integral, for example. So the proof is straightforward. You just multiply this out using geometric series and integrate term by term. So the generalization of this is conjectural, and we expect that special values of, I guess I should use the adjective motivic here, zeta and L functions are also expected to be periods, or conjecturally periods. So the theory of values of L functions is a subset of a subclass of periods. Okay, quickly for a family, let's just do a simple example. Here's a family of periods. I'll write it this way. A family of periods is a very basic example. The logarithm function. So first of all, we take y to be we think of it as a real number, and we can integrate. Well, first of all, we can take it to be a rational bigger than 1, and then it's simply this number is a period according to the first definition. But then we can say, well, let's allow y to move around, and then it defines. Think of it as a function, and what we see is that this has an analytic continuation. So a priori, this inequality only makes sense if y is real, but you can analytically continue this into the complex plane, and it defines a multi-valued function. So some people call this like a period function or something, and I don't like that very much. So this multi-valued is of course known to everybody. If y winds around the origin, then log y gets modified by 2 pi I. Okay. So this, okay, so here's a more a definition that's better suited to most purposes. So now let's take X, a smooth algebraic variety, algebraic over Q. And let me take omega, a regular, what did I say? N form, doesn't matter. N form on X over Q, defined over Q. So if X is affine, then you might want to take a globally defined algebraic differential form. If X is not affine, I'll explain in a minute what you mean by this, but omega will be a collection of of differential forms on a affine covering. But then you can consider integrals of this type. You can integrate omega over a chain so gamma is a chain. So in general, what this means is that omega is a collection of forms, and you have to integrate. You take this integral as a sum of integrals over different patches. Okay, but let's ignore that for now. And what we can do here is we can allow this chain to have a boundary. So delta of gamma can be contained in the complex points of D, where D will be a subvariety, a divisor, I guess, of cohomology 1, but also defined over Q. So that's a better definition of a period. And for families of periods, it's the obvious thing. We consider not varieties over Q, but families over some base. And the definition is fairly clear. Okay, so the point of this is that structures and features, not sure how to say this, of the cohomology of algebraic varieties aka and motives, show up as structures and features of periods. So I don't know, properties of periods. So what's nice about this is that periods give you a very elementary way to view some of the deep theorems and conjectures in the theory of motives. And conversely, they give applications of that theory to other branches of mathematics. Let me name quickly just a couple of examples, and I may or may not explain them in more detail in the course of these lectures, depending on time. So one is that the cohomology of algebraic varieties have mixed Hodge structures. And Hodge, in mixed Hodge theory, you have a notion of weight. And that leads to a notion of weight for periods. So periods have weights. And that's a very nice way to think about weights. What else? We have, there's the whole Tannakian machine. We have Mumford-Tate groups, or in some settings, Motivic-Galois groups. And these show up as extra structures on periods. You can set up sort of groups acting on periods. Or some versions of periods, I'm being a bit sloppy here, which generalize the action of the classical Galois group on algebraic numbers. And I'll just drop the word in case I don't have time to say anything about this. This shows up at something called a coaction, which is used very heavily by physicists, so it's something that will come up again for sure. And also, we've mentioned motivic cohomology in K-theory. And this completely determines the structure of the space of periods. So, sorry? You're not saying no, absolutely not. No. On some version of periods, which I will get to. Yeah. Yeah. Okay. Yeah, this is a kind of spoiler. And motivic cohomology and K-theory determines, at least conjecturally, determines the structure of the ring of periods. So it controls the structure of the ring of periods. So if you could magically make K-theory groups smaller, then you'd create a lot of relations between periods. And so on and so forth. Okay, so the beyond in my title referred to where my heart lies, what I'd really like to talk about, which are variants of this theory and new directions in which to take it. And a lot of this is very much inspired by recent developments in mathematical physics. Okay, so the first is still fairly and squarely within the theory of periods and cohomology of algebraic varieties. So I'm not changing much there for now. And these are what you could call dz bar integrals. So they're anti-holomorphic. They're integrals which involve anti-holomorphic as well as holomorphic forms.
Sorry.
Yeah.
I'm lagging. What do you mean by regular form?
I'll write down a definition later. I'll come to that. It'll be a section of the sheaf of Kähler differentials on X in the case when X is affine. Can I return to a question? I will get there. So dz bar. So this is joint work with Clément Dupont. So in many applications, you find yourself faced with integrals of this type, where you're integrating over the complex points of an algebraic variety of a holomorphic, an algebraic differential form, wedge, the complex conjugate of another algebraic differential form. Now, of course, when x is projective, then and omega nu have no singularities, then this is something very classical. We see it already in the Riemann bilinear relations, for example, are proved using this kind of idea. But here we're going to allow them to have singularities. And this is a can of worms, because these integrals in general do not make any sense. So I recommend there are a couple of papers by Kasdan and Felder on this, who were inspired by problems in string theory and trying to make sense of them. These integrals are ill-defined in general, but there is a setting in which they are well-defined, which I will explain next time. And it turns out that these are, in fact, periods. So this is very surprising because these do not look anything like the sorts of integrals we had before. And it turns out that they are very special types of periods. So there are conditions on omega nu for this to make sense, but I'll get to that when it comes to it. This is, well, this is the overview. It doesn't have to be no. I mean, the non-compactness is contained in the word singularities here. You can think of it as compact if you like. So let's just give so what I'm going to do now in this section is just throw out some topics and give just one example of each, because these are the things I'd like to put on the table, and they will definitely come up at later points in the workshop. So here's an example, 1 over 2 pi I, integral over c dz over z minus y minus dz over z minus 1, wedge dz bar over z bar. And this differential form here is somehow playing the role of this interval 1 less than x less than y. You can see the y and the and so you can see that it's not very difficult to verify that this integral is actually log of absolute value of y squared, which is twice the real part of log of y. Okay, and because 2 pi I is an imaginary number, this quantity is well defined and it's single valued. And in fact, we should all recognize it because it goes into the definition of the Dirichlet regulator. So this theory has a name. It's we call it single-valued integration. And it turns out that integrals of this form pick out a very particular subclass of periods, which are very interesting. So examples of this include the theory of regulators, also the theory of heights. So here I'm just picking words in the titles of the conferences that are coming up later on. And from a physicist, from the physics perspective, excuse me, these are what physicists refer to as closed amplitudes. In case you're wondering. Okay, so that's one topic I would like to talk about. Here are a couple more. So here's something else that goes. So this is just this single valued integration is just part of the theory of motives. It's really a p-adic integral where p is the infinite prime. So there's nothing fundamentally new on this side that corresponds to it. But something else that, again, the physicists have been pushing a lot, which I find very exciting, is the theory of Menon transforms. And there's a little bit of work. I have a preprint on this with Clément Dupont again, and some joint work in progress with Dupont, Frezan, and Tapuskovic. And here, you want to understand objects of the following kind. They're period integrals as before, except now you decorate them with some functions raised to some powers. So here again, gamma is a chain which may have a boundary. So okay, what's the example? So let me explain just on one example why this is interesting and why this goes beyond the theory of motives as we currently know it, as we usually know it. So examples include the hypergeometric functions. And I'm going to now just write down the example of the beta function. So the beta function, of course, is extremely old. And it is, I'm going to write it in a slightly funny normalization, S1 integral from 0 to 1, x to the S1, 1 minus the x1, oh sorry, x0. Hope my sign's correct. I beg your pardon? No, this is the key point. So, no, the answer is no. And the key point is that I want to view SI as I want to view this as a function of the SIs. So yeah, thank you actually, because so there is the theory of hypergeometric motives, a very interesting theory of hypergeometric motives. What we normally do is we fix a value of SI, typically a rational number or something, and then absolutely that defines some family of algebraic varieties. But we want to do something completely orthogonal and allow the SIs to change. Right? And that's a very weird thing to do from a classical algebraic geometry perspective. And I'll tell you why it's weird and what the miracle is.
Is S0 related to S2?
Oh, sorry, yeah. No, you're right. It's actually, this was 1 and 2. What I wrote the first time was correct. Thank you. And of course, so this is a quotient of gamma functions. So this is something that that's all the rage in high-energy physics community at the moment, and they're the ones who've come up with these conjectures that I think are absolutely extraordinary. Yeah, it's slightly modified beta. Yeah, you're right. I should give it a different name, shouldn't I? Yeah, beta twaddle. Thank you. So very classical formulas that, so what's this got to do with periods? Well, not a lot it seems, but if you expand it, you find it's actually a generating series of periods. Right. Out of chalk. So it's a generating series of periods. And these periods, zeta n, are periods of completely unrelated algebraic varieties. These periods are very different to each other. for example, from the K-theoretic point of view, zeta 3 corresponds to K5, and zeta 5 corresponds to K9. But there is a sense in which you want to think of this beta function as being attached to a motive. And the only reasonable definition is that that motive should be rank 1. And if that's the case, if that theory is to make any sense at all, that means that, for example, that the motivic Galois group is going to act on this in an incredibly simple way. And it's going to have to act on all the zetas in exactly the same way. And that's true. It's completely extraordinary. So this observation, again, found by physicists, is that something extraordinary happens here when you expand in these variables. You somehow tie together an infinite family of periods in some mysterious way. And we have a preprint with Dupont in which we proved some of their conjectures because I didn't see any good reason for them to be true at all at first. But it looks like there is a theory there beneath the surface. Sorry?
Do you want to say or later what this remarkable property is?
Yeah, well, I'm concerned about time. I'm sort of laying a menu of things that I would like to talk about.
That there's a special property, say that n is.
Maybe in my third lecture I'll be able to explain what it is. Yeah. So what's going on here is if you were to fix the values of the SIs, you're really looking at cohomology with coefficients, or twisted cohomology. So that means you're looking at homology with coefficients in a local system, or de Rham cohomology with coefficients in an algebraic vector bundle with connection. But what we really want here, we want to allow the SIs to move. So we want to allow the SI to be variables. And you want, in particular, to take Taylor expansions. Okay, so since maybe I'll say it. Okay, so where does this come from? I guess I should, part of the purpose of this sort of overview is so that those of you who do attend the conference on mathematical physics can situate the concepts in the mathematical landscape. So one thing that physicists do a lot is they do something called dimensional regularization, which is where this comes from. Regularization. And that's where you consider, very informally, some integrals p over q to some power d in the Kontsevich-Zagier setting of the very beginning. And for a physicist, d will be the dimension of space-time. But when d equals 4, this integral diverges. So what they call dimensional regularization is replacing d with something like 4 minus epsilon and expanding in epsilon. And they want to consider this as a series in epsilon. And that's not directly connected to the theory of motives as we know it. It's really considering infinite families of motives simultaneously in some way. Okay. Related to this, in this context, I should mention something which is closely related, superficially related, but actually quite different. This is also something that's very exciting, but about which I will say nothing. So a related concept is the notion of exponential periods, and recently exponential motives. So this was worked on in the early days mainly by Kontsevich, and there's recent work by Frezin and Jossen. And superficially it looks quite similar. You take an algebraic variety and a morphism to GM, I don't want to say anything about this, so let me just take one such map. And you're studying integrals of this form, e to the minus f. So the input data is superficially the same, but the objects are very different. So Kontsevich has studied this extensively, and now there's a notion of exponential motives and Galois groups and so on, with some beautiful applications which underlies this. Yeah, good question. Maybe it's A1. Yeah. I don't know. Yeah. Yeah. I'm sure A1 is fine. I don't know why I wrote GM. Maybe a hangover from notes, previous notes. I think you're right. Okay, finally, something else that, if one had the time, it would be nice to talk about. So this is something that's very recent that I worked on last year, and I believe there's a lot of stuff to be worked out here. And a general philosophy of which I'm sure we'll see a lot this week is that special values of L functions var conjectures of Bailenson, Deligne, and a great deal many other people who are sitting in this audience, I shan't embarrass, should correspond to very special classes of periods. And these should be periods of very simple types of motives, so pure motives or simple extensions, possibly bi-extensions. So I believe very strongly that there should be a much larger picture here, general periods, that it's possible to extend this enormously. So much more general class of periods, possibly of all motives. Again, this is very preliminary. Should be related. There should be something that sits here that predicts periods of much more general motives. So there should be some special values of mixed L functions, whatever they are. But there's an increasing body of evidence that such a thing can be made to work, and I think this is where a lot of the future lies. So the underlying mantra here is: can we find formulae for periods by counting solutions to equations over finite fields. So that's the general theme. Okay, so those are some things that I just wanted to put on the table. And I very much doubt I will have time to even cover a fraction of them. But I'm sure that they will come up in the later conferences. Okay, so now back to classical periods. So that's the end of the overview. Okay, so now let X, so back to the initial setup. X is going to be a smooth algebraic variety over Q. And Grothendieck defined the algebraic de Rham cohomology we can work over any field of characteristic 0. I'm just going to take Q to make my life easier. So Grundig defined the algebraic Durham cohomology to be the hypercohomology of X with coefficient in the sheaf of Cayley differentials. So this is Grothendieck 66. Oh, sorry, 64. So this is something very concrete if X is affine. And suppose it's of dimension m. Then we can write this down. In this particular case, you can express this very simply. We can take the following complex of global sections. What was it, M? All right, so these are global, regular, 0 forms, 1 forms, M forms. And the maps here are a differentiation, D. And so gamma xi equals global regular I forms on X over Q, of course. I think it's over Q. And HM, sorry, what do I call it? HN. In this case, HN Durham equals the nth cohomology of this complex. Okay, so it's a finite dimensional vector space over Q. So maybe a quick example. If we take x equals gm, then this complex is simply 0. The 0 forms are just the regular functions on gm, and then the 1 forms this, and it stops there. All right, so we get h0 Durham gm is q, and h1 Durham is isomorphic to is rank 1 generated by dx over x. Okay, so this is something very concrete. In general, if x is has a covering by open affines, then you form a double complex in the usual manner. And I'm going to skip it because I'm running a bit behind time. I was also going to recall Durham's theorem from 1931, maybe in a couple of words. So Durham in 1931 showed that for M, a smooth, compact, orientable manifold that what he defined as the Durham cohomology, but I'm going to call it dr analytic. In this context, it's clear, but for an algebraic variety, you need to specify. He showed that there's an isomorphism between what he defined to be the Durham cohomology and the Betti cohomology. Okay, so this he defined the Dram cohomology to be closed C infinity I forms modulo exact, smooth I forms. And here the Betti cohomology is the dual, since coefficients are in Q, this is just the dual of the homology. And the homology is given by closed I chains modulo boundaries. Okay, so then the starting point for the theory of periods is following theorem due to Grothendieck. So this is singular homology. This is singular cohomology. Right, and I should say, so that what is the isomorphism here? Well, you take it's just given by integration. So you take a closed C infinity I form here, and you take a closed topological chain of dimension I, and you can simply integrate omega along gamma. And the observation, due to Durham in his thesis, is that, of course, this makes sense. This only depends on the cohomology class of omega and the homology class of gamma because of Stokes' theorem. So then you can turn that this, and then the theorem is that this is if you tensor this with C, it becomes a perfect pairing of C, and that means that you can move this across and get this isomorphism. And the isomorphism is, to the class of omega, you associate the functional gamma goes to integral gamma of omega. And that's well defined on cohomology classes and homology classes, respectively. Okay. So then Grothendieck comes along and explains how to generalize this to oh, too many brackets. Oh yeah. Well, I mean, it makes by that it makes sense, but if you don't like it, I'm very happy to get rid of them. If you care about it, okay. Good. So Grothendieck then. So that's for a smooth, compact manifold. So it's clear in that case that the vector space, that the groups are finite dimensional. So Grothendieck then understands how to explain this how to extend this to first of all the algebraic case, and also the case where it's not compact. So I guess Grothendieck's result, just watching the clock, Grothendieck's result, which is plus Serre-Gaga. Well, let me just skip it. Let me just say, let's take X, smooth algebraic over Q as before. But it works over any field of characteristic 0. That's not a problem. Then there exists a canonical isomorphism, which we call comp. This is Dedin who calls it comp B Durham. It's a very good notation. From the algebraic Durham cohomology tensored with C to the singular homology. singular cohomology of the complex points tensored with C. So that's an isomorphism, and again the map's the same one. It's integration, given by integration. It does it by showing, well, it's a long story. Okay, so the first point is that this is natural. In other words, it is functorial with respect to morphisms. And it's an isomorphism between two vector spaces over Q of finite dimension, which is a consequence of this theorem due to Grothendieck. So the point is that once you have a rational structure, if you just have de Rhams theorem, there's no way to talk about periods because the de Rham cohomology is only defined over C. So there's no way to have there's no Q structure. There's no way to speak about periods in this context. But once you have a Q structure, this is Grothendieck's insight, then you have a notion of period. So according to Grothendieck, a period is where we choose a Q basis of HI de Rham XQ and a Q basis of the singular homology then you can write this comparison isomorphism in this basis. And you get a matrix. And so we get a matrix which is called the period matrix relative to these bases. So its entries are periods. No. That's the whole point, that it doesn't need to be compact. Yeah. Actually, maybe I can do. Yeah, maybe I'll do C star then. Do that quickly. So I should. So it's very important here. I should say this because you seem to be listening. It's very important that the comparison isomorphism goes from de Rham to Betti. It's because we integrate differential forms over chains. We don't integrate vector fields over co-differential, co-differential forms over co-chains or something. And part of the difficulty in the regulated part of the difficulty in relating the theory of L functions into this periods framework is that the isomorphism is systematically written in the other way. And when you invert this matrix, that wreaks havoc with all the weights and so on. So maybe that's a psychological difficulty, but I thought I should mention that. It is important that it goes from de Rham to Betti. Okay, so example 1. Maybe I just have time to do this. So let's go back to x equals gm. The homology of the complex points of x, or we can work with z coefficients, but let's just q, is one-dimensional, spanned by, so the complex points of x is topologically a circle, as we saw already in Vesner's talk. So we have a chain here. We just saw that H1 de Rham, GM is one-dimensional spanned by the class of dx over x, because that's a regular differential form that doesn't have, that it's not D of something algebraic. And so the comparison isomorphism sorry, I haven't used that notation yet. Yep.
Q dot dx of x. It's not polynomial.
Q dot, well, this is the class Q, the vector space times, oh yeah, dot, I see what you mean. Yeah, sorry, it's later in the day. Yeah, okay, that makes sense, yeah, that's good. And so it takes the class dx over x to the function which assigns dx over x over gamma naught, and by Cauchy this is 2 pi I. So in this basis, the period matrix is 1 by 1. It's just a 1 by 1 matrix with the entry 2 pi I. Okay, fine. And now, since it's late, I'm good to do a very, very familiar example, so I'll need it next time, just of an elliptic curve, and call it a day. So the beta function I alluded to earlier is exactly the same as this. The beta function is like an analog of 2 pi I somehow. It's a rank 1 object. So here the rank is the dimension of these vector spaces. So you've got the algebraic Durham cohomology, you've got the singular cohomology, you've got the L-adic cohomology, you've got all sorts of realizations. And I guess Grundig's observation was that they all behave the same way. And in particular, they have the same rank, aka dimension over the appropriate ring. So this is rank 1, it's one-dimensional, so it's a 1 by 1 matrix. So example 2, again super classical. Let's take E to be a plane elliptic curve. Let's take this, and so let's again take UV in Q and the discriminant. So I should maybe have said something back here. So in the general case, since I'm working over Q all the time, but I mean it's no problem to work over K. The point is that if you take K, any field of characteristic 0, what you want is it to be embedded in C in order to be able to define the complex points of X relative to that embedding, and that's important. Okay, just to say that there's no difficulty in working over more general, over number fields, for example. So let's consider the punctured elliptic curve, E minus infinity. So infinity is the point 0, 1, 0 in projective coordinates. And this doesn't, removing a point doesn't change the cohomology. So there's a restriction map to E prime. And this is part of a Geisen sequence, so there's the residue, a Tate twist, and this is isomorphic to H2. But in any case, the point is that this is an isomorphism. So we can replace the cohomology of E with the cohomology of E prime. Nothing changes. And now E prime is affine. So it's a nice exercise if you've not done it before, to use the Grothendieck's definition of the algebraic Durand cohomology as this complex which I've erased, and you can convince yourself that the algebraic Durand cohomology is of rank 2, two-dimensional, spanned by two classes, the holomorphic differential and a differential of the second kind. So it's a two-dimensional vector space. So sort of spoiler for what's coming later on. There's also something called a Hodge filtration on this vector space. This spans F1 and F0 is the whole two-dimensional shebang. Maybe I'll keep that. Let's get rid of this. So of course, as we all know, that the complex points of the elliptic curve is isomorphic to the quotient of the complex numbers marked by a lattice. So it's a torus. And on this torus we can pick our favorite closed cycles, alpha and beta. And the singular homology so there's a little niggle here that you've got to make sure that since we're working with the affine curve, you've got to make sure that your cycles don't pass through the removed point. Sounds stupid, but you'd be surprised. So this is a two-dimensional vector space spanned by the class of alpha and the class of beta. And we get a period matrix, which is a 2 by 2 period matrix. Incredibly classical. And you integrate the holomorphic differential form over alpha and over beta, and the differential over the second kind of alpha beta. So the numbers in this column are classically called periods. Oh, that's purple, that's not good. These numbers are called periods. The numbers in this column are called quasi-periods. And I guess an important point here is that the numbers in this column are well defined up to multiplication. And that's because this choice of holomorphic differential is unique up to multiplying by a non-trivial rational number, whereas this... No, so it's well defined because... oh, yeah, with respect to this, yeah, sure. Okay, what we can do as well, because E is over Q... Yeah, okay, thanks. Because E is defined over Q, we can actually... Maybe I'll park that later, yeah. Absolutely right. The point is, okay, what you said is absolutely correct. This column, however, is not well defined because this differential of the second kind is not a priori well defined. I mean, in these particular coordinates, we've chosen to put our singularity at the point infinity, but we could have chosen another point. And as we shall see tomorrow, on Wednesday, when I discuss heights, that's a key point, that these things are not necessarily well defined. And you can add a multiple of this column to that column, because this differential form is ambiguous up to adding a multiple of the holomorphic differential. Now you can make it much more rigid again by looking at the action of complex conjugation. Complex conjugation acts on this singular homology. That's because this equation is defined over Q, and so complex conjugation is an involution, and so it decomposes this space into eigenspaces, and you can choose a basis. You can assume that alpha is plus invariant, so it's a real cycle, and beta is minus invariant. And then actually that will fix the rows as well in answer to Don's question. And I guess that the theory of regulators is well, the business of regulators is kind of is in the spirit. It says you've got this period matrix which is ill-defined. It depends on choices of bases. But what are the quantities that you can construct out of it which are well-defined? So you have these extra filtrations. You have a Hodge filtration, a weight filtration. You have this complex conjugation. Using all of that, can you cook up things out of this matrix that don't depend on choices? And those are the things which turn out to be related to L functions. Okay, so just final remark, because I'll need this. Of course, omega 2 is tau omega 1, as everybody knows. That the modulus, the tau is the ratio of the two periods. There's the Legendre equation. If my normalizations are correct, then this should be exactly 2 pi I. And then there's a result which I think is due to Fricker, but I can't find the original reference, that relates the two quasi-periods to the classical period tau. So if you compute omega 1 eta 1, the product of the period and the quasi-period over 2 pi I squared, then since the elliptic curve is actually determined by tau, then you expect a relation between these quantities, and in fact this is G2 of tau. So G2 of tau is the Eisenstein series of weight 2. Sigma 1 is the divisor function. So yeah, thank you, minus. It's late. 1 over 24 plus Q 3Q squared plus dot dot dot. So this is all extremely classical. This is not a modular form. It's the Eisenstein series of weight 2. I'll stop there. Hello.
Yeah. So when you introduced the PM methods, my expectation was that the coefficients would be periods. So currently some of them are periods.
Oh, sorry, they are periods. Sorry, sorry, it's late in the day. I'm not explaining what I meant to explain. Classically, these are called periods and these are called quasi-periods. And then Grothendieck, in a footnote in his paper, says, well, these are all sort of periods because the definition is the same. And Kontsevich and Zagier formalized this word within the title of their paper, and they said, well, periods is more general still. It's any integral of this kind, but you're also allowed a boundary. So classically, the chains of integration have no boundary, but you should allow yourself a boundary. So periods is the big box, and quasi-periods is a type of period, unfortunately. Yeah.
Actually, that question leads to mine, because the recent periods are called periods. It's because they generalize the classical periods. But the recent classical periods are called periods because the elliptic functions are doubly periodic. They are actually series in something.
Yes.
So the question is in what more general context besides say Boolean varieties, is that true that any kind of period occurs as a periodicity of some function?
That's a good question. Let me think about that.
But here there's kind of
Yeah.
it is common that
Yeah, I think the origin of a period comes from the period of a pendulum or a period of a planetary orbit in the elliptic context.
from the fact that it's doubly
Or periodic. Oh, I thought it came from the... I thought...
it's just like X, that also is a period. This is double period.
Okay.
So those are true periods, in that something is invariant under translation by omega 1 and by omega 2. But nothing is invariant by translation under eta 1 or eta 2. So these numbers are not periods in that very classical sense.
Yes.
And that just asks whether any other periods in the modern sense that are periods in the classical sense. Like the other period is something. It's a stupid question.
I'll think about it. I shall honour your stupid question with a pause for reflection.